So today we are talking about intermolecular interactions or intermolecular forces. So science recognizes three stable phases. The solid phase, in which individual particles can be thought of as a contact and held in place, right? So this is an example of how mm, particles in a solid phase can be inside. The liquid phase, molecules packed close together, but they free to move, comparing to the solid because they are packed very tight and fixed. So they are almost not moving in a solid phase, right? So, and gas phase, in which individual particles are separated from each other by relatively large distance, usually the distance between much larger, as in this picture, and uh, no, and moving in a gas phase is very fast. So, not all substances will readily exhibit all phases. For example, carbon dioxide does not exhibit a liquid phase, only gas and solid, unless the pressure is greater than about six times normal atmospheric pressure. And as you can see in this picture, again, we can repeat what terms we can use um, to describe conversion from one phase to another phase. To go from solid to liquid phase, it is melting. Uh, to become liquid into gas phase, you need to evaporate or vaporize, right? To go back from gas to liquid, it's condensing. To go from liquid to solid, it is freezing. And to go from solid to gas, it's sublimation. So this chart gives us information about temperature ranges for the three phases of various substances. And you can see that these are three substances here: hydrogen, water, and sodium chloride. So hydrogen, water, and sodium chloride. And you can see that solid phase for hydrogen begins at negative 259 degrees in Celsius, and gas phase is above 253 degrees in Celsius. For water, is gas phase is 100 degrees in Celsius, and for sodium chlorides is 1,013 degrees in Celsius. So you can see that there are much variability. Why do some substances become liquids at very low temperatures while others require very high temperatures before they become liquids? It all depends on the strength of the intermolecular interactions between the particles of substances. Although ionic compounds are not composed of discrete molecules, we will still use the term intermolecular to include interactions between the ions in such compounds. So, substances that experience strong intermolecular interactions require higher temperature to become liquid and finally gases. Substances that experience weak intermolecular interactions do not need much energy to become liquids and gases and will exhibit their phases at lower temperatures. So you can see that it's true for hydrogen, and see that sodium chloride is a kind of substance that experience strong intermolecular interactions according to high interface temperature. So substances with the highest melting and boiling points have ionic compounds, ionic bonds, I'm sorry, or sometimes it's very rare, but sometimes they have covalent network bonding. So this type of intermolecular interaction is actually a covalent bond between atoms. In these substances, all the atoms in a sample are covalently bonded to other atoms. In effect, the entire sample is essentially one large molecule. Many of these substances are solid over a large temperature range because it takes a lot of energy to disrupt all the covalent bonds at once. One example of a substance that shows covalent network bonding is diamond. So we can put data about diamond here. Diamond. And temperatures over 3500 degrees in Celsius, diamond finally vaporizes into gas phase atoms. So, and you can compare this temperature to this, and even this, right? So, this is a very high temperature. So the next strong force between any two particles is the ionic bond, in which two ions of opposite charge are attracted to each other. And as an example, we have sodium chloride here. So two opposite charged ions, sodium positively charged and chlorine negatively charged, I'm sorry, negatively charged, and they strongly attracted to each other. And that's why the temperature to jump from one phase to another phase is pretty high too, right? So strong intermolecular forces between particles, between units, the high temperature for changing phases. So, ionic interactions between particles are another type of intermolecular interaction. Substances that contain ionic interactions are relatively strongly held together. So these substances typically have high melting and boiling points. Most substances that experience covalent bonding exist as discrete molecules. And here are two examples of discrete molecules with covalent bonds inside. So this is hydrogen and water. And you know that hydrogen is a typical non-polar molecule and water is typical polar. Right? So it's not symmetrical and it has unshared pairs, lone pairs. So that's why, and it has polar covalent bonds. So that's why this molecule is polar, right? So two types of covalent compounds in front of us: hydrogen, non-polar bonds, non-polar molecules; water, polar bonds, and polar molecules. So as you can see, the difference between temperatures for changing phases. So For hydrogen with nonpolar molecules, temperature is very low compared to water. So, these are examples of polar or non-polar molecules with non-polar or polar covalent bonds. So this is methane, the first one. So carbon bonded with four hydrogens, and the delta of electronegativity here is less. Electronegativity is less than 0.4. That makes bonds between carbon and hydrogen nonpolar. So nonpolar bonds. Nonpolar bonds. And if molecule has nonpolar bonds, it automatically makes this molecule nonpolar. So nonpolar molecule. This HF. So we know that electronegativity of fluorine is about 4, and it's about 2.1 for hydrogen. So the difference is very high. That makes this bond between hydrogen and fluorine is very polar, right? So we have delta negative charge on fluorine and delta positive charge on hydrogen. So, and there are 3 lone pairs for fluorine here. So, and you can see this molecule is very polar, right? The next one, CO2, carbon dioxide. It has polar bonds here, but molecule is, oh, I'm sorry. Eraser and pen. It has 2 slightly negative oxygen and 1 delta positive carbon. But this molecular is non-polar because their effects cancel out because of the spatial orientation of the bonds in each molecule. And as a result, such molecular as a carbon dioxide and such molecular as a carbon tetrachloride, CCl4, right? Non-polar, even they have polar bonds. So these are two types of molecules, right? So non-polar, maybe 3 types, let's say 3 types. Non-polar with non-polar bonds, right? So these are non-polar with polar bonds. And this one is polar. And of course with polar bond. So if we have polar molecules with HF or OH or NH bonds, which are very strongly polar, in molecules that have these bonds, particularly strong dipole-dipole interactions can occur. What does mean dipole-dipole, right? So we see that this is negative, this is positive charges, and it's not symmetrical. That's why this part of water molecular is attracted to this part. So delta positive charge part is attracted to delta negative part. So so that is interaction, intermolecular dipole-dipole interactions. And these dipole-dipole interactions add something in physical properties of this compound, and that makes the temperature, like melting temperature or boiling temperature of water, higher than a temperature, boiling temperature of hydrogen, let's say. Between hydrogen molecules, there are no such interaction. Such interaction, like between water molecules, is called hydrogen bonding. So, hydrogen bonding, it's not, let's say, again, so H2 has hydrogen, but between between these kind of molecules, there are no hydrogen bonding here because there are no charges, non-polar molecules, right? And here we have hydrogen, which is delta positive, and we have a delta negative atom which attracted to this hydrogen. That is hydrogen bonding. So the presence of hydrogen bonding between molecules like water can have a large impact on the physical properties of a substance. And you can see that another picture which shows us how hydrogen bond forms between water molecules. You can see that this is hydrogen, delta positive, and this is oxygen, delta negative, and this is a kind of attraction between them because of their opposite charges, right? So but hydrogen bond not only can be between like similar molecules, like between water molecules, so it can be between like water and ammonia. And I can repeat, so we need to have in our compound to have hydrogen bonds, we need to have these like parts of molecules. We need like HF part or bond or HO or HN. And you can say water have OH, right? So polar covalent bond here, and here we have NH and N nitrogen in ammonia is negatively charged and hydrogen is positively charged. And it's enough to forming hydrogen bonds too. So again, intermolecular forces like hydrogen bond are forming between polar molecules which have this kind of bonding inside.